Last one.
Yeah,
Yeah,
that's right. Yeah.
the tutorial is coming back to the cheaper.
I guess we have a pointer. So it's my last lecture, the third one of three. So today I want to extend the discussion that we've had in the first two lectures to the epoch of reionization. Can understand what complications arise when we move from the simple physics of cosmic dawn, where the simple is of course in double inverted commas, given the complexity of Laminar physics that we have seen in the first two lectures. Okay? Now, the first thing to remind ourselves is what we have discussed so far. So again, what we have been talking about is the relationship between some physics parameters and some observables, and we call that establishment of those relationships modeling. And then the opposite process is that of inference, where we have a measurement and then we guess the value of the physics parameters given a model using principles of statistics and probability. Now, yesterday, what we have done is we have set up equations for a complete physical relationship from the main 21 centimeter observable, namely the T21 or delta TB, the brightness temperature, to the parameters that decide the Lyman alpha coupling and the collisional coupling. Right? We highlighted the dependence of the cosmological parameter. We highlighted the dependence on galaxy formation parameters such as F star and so on. This was just one model. You can write different models by replacing the details of galaxy formation in the last lecture to change to whatever your favorite way of forming galaxies is. Okay, but the thing to notice there was we actually postulated a way in which galaxies form. We actually postulated a way in which halos form, halos grow. They start hosting galaxies. These galaxies start hosting stars, and these stars produce Lyman alpha cota. Okay, the whole thing was written down by us as a postulate, and then used it to derive the 21 centimeter signal. What I wanted to start today's discussion today was basically to contrast that whole approach with an approach called empirical modeling, where we actually don't do that, or at least avoid doing such postulating as much as possible. Okay? So the discussion should begin with the edges measurement, because edges really, we all know there are issues with edges measurement and so on, but edges measurement really shows the limitations of the way we did our modeling in the first lecture. Okay? So what is shown here, I hope everyone can see this. I have just recycled slides from some talks. I didn't have time to increase the font size and so on. I'm afraid for this screen. But what is shown in this right hand side panel is the 21 centimeter observable delta TB, now globally averaged, the kind that Saurabh and Kanan are discussing in this school, as a function of redshift Z. Okay, the redshift goes here in this particular plot from 26 to 40, and the delta TB has values of a few hundreds of millikelvin, as we have seen in Kanan's lecture. And this dashed black curve with the gray band is the edges measurement. Okay, whether you agree or disagree with that, that's their measurement. Now, Saurabh, I think, had a very nice plot. Was in his talk in Guwahati last week. I don't know if he's shown it here yet, where he shows how different this measurement is from any value of the standard model. Any point in the parameter space, it looks qualitatively different, right? What are the differences? The depth, as everyone probably knows, is much greater than anything predicted by the standard model at this redshift. But now this plot highlights a second difference, which actually very few people have discussed, and that is the difference in the shape. Okay, so what is shown here is in green is a model that tries to match the depth by adding an extra radio background, something that Shikhar I think did this morning, or at least discussed this morning. And so that depth problem is solved if you allow the model to have an extra radio background. But you can see that even in that case, the best fit model is a really bad fit to the edges data. The edges measurement gives us a 21 centimeter absorption curve, which is very boxy, what they call in their paper a flat bottom Gaussian. But all theoretical predictions are almost like a normal Gaussian, right? Now you see, every single theoretical calculation is missing this shape. But there is intrinsically nothing wrong, nothing that prevents the 21 centimeter absorption from this shape. And in fact, then this raises the question, what other shapes could there be in the real absorption? Suppose edges is wrong. At least edges is highlighting this issue that there is absolutely no reason for us to be biased or prejudiced in favor of only these particular classes of shapes, right? And so this is the motivation for empirical modeling. And so I will show you an example of how empirical modeling works. Just like our parametric modeling of lecture number 2, empirical modelings are also of a diverse class. You can change the details of empirical modeling, but the basic philosophy of what I am going to present always holds. So what empirical modeling does is it tries to use the data itself to read out the parameters for which we postulated a galaxy formation model. Okay, so for example, in this case, what we do is we actually start by asking, what is my basic equation? We know that my basic equation is this. We have written this equation down multiple times in this school now. This is the delta TV, and here are these various parameters, and we said that the most interesting term is this 1 minus TR by TS, where this TS also we have written down. The equation looks like this, right? Now here basically these are the equations. Now in a parametric modeling effort, which we did in lectures 1 and 2, we actually computed these things in a particular model. But I hope everyone agrees with me that that model is heavily prejudiced. No one has told me that stars and galaxies should be the way I wrote them down in that model, at these redshifts in particular, where we haven't seen any stars and galaxies yet. So I had actually no right to write down the model that I wrote in lecture. So instead, what I do now is don't do it. I don't actually write a model like that. Instead, what I do is I start inverting the data. So I remain agnostic. I say, okay, I don't know anything about how X alpha is, how F star is, blah, blah, blah. Let me see what the data requires. Okay? And then I will worry about whether I understand what comes out later. So here, for example, what happens now is the expression connecting delta T B, the observable, to the spin temperature, we can invert and write this down as an expression between the spin temperature and the observed value. So for a given observed value of the delta TB, we can now ask what is the spin temperature that the data requires. And then we get some spin temperature. Now suppose I want to ask, well, what is the Lyman alpha coupling that this spin temperature requires? So everything else kept the same. Suppose I still do parametric modeling for my X-ray heating. Let's just imagine, we can relax that also. But suppose I keep everything else the same. I just want to ask, how does the Lyman alpha term evolve? That whole complicated calculation that I wrote down in the last 2 lectures. Well, what I can do is I can now invert the spin temperature dependence on the X alpha. Okay, under the assumption here that my TK is the T spin is the T color is TK, the color temperature is kinetic temperature. So I've ignored Lyman alpha heating for the moment, but I can now write X alpha in this form. And now what I can do is I can start with some 0th approximation for my J alpha, the Lyman alpha flux, which decides X alpha. Okay, the story so far is the observer gave us some delta TB, we inverted them and got some spin temperature, we inverted that and got some X alpha. Now what do I have to do? X alpha is decided by J alpha. the flux which is produced by galaxies. So I need to know J alpha. So there is various way, and this way actually Shikhar invented. Here, the way this works is in an iterative fashion. What Shikhar says we should do is he says we should take a zeroth order approximation for J alpha. This could be any favorite J alpha. This could be our yesterday's J alpha. And then you plug into this equation. What you do is you take that J alpha, multiply by the X alpha prime that is desired, divide it by the X alpha that corresponds to that J alpha. So you update it. And this J alpha prime would be closer to the J alpha that gives this correct X alpha. Okay, and you keep doing this, and then you will converge. It's not at all obvious that you will converge to the correct J alpha, but luckily Shikhar found that you quickly converge to the J alpha. That is right. And then what you can ask is, well, for that J alpha, what is the correct epsilon alpha, the volume emissivity? J alpha is still the flux, the specific intensity of UV photons. Well, I want to know now what is the volume emissivity of UV photons that gives that specific intensity. And then what you can do is you can again solve that. That turns out to be a very similar iterative process. But here what we did was we added a multiplicative factor to the epsilon alpha and solved for that multiplicative factor. So we said that, okay, my default epsilon alpha is from my postulated model of lecture 2. And now I ask, by what factor does it have to be multiplied so that I get the correct epsilon alpha corresponding to J alpha. So is everyone following the logic, the dependence? You start from the observed delta TB, you get TS, you get X alpha, you get J alpha, and now you get the epsilon alpha. Okay, but notice that you are not postulating a model, you are reading out the model that is required directly from the data. If the data is now weird, the model will be weird. Okay, and here is an example of what happens. Before I show you what comes out, here is the model prediction that comes. Here again you are seeing that edges measurement. This focus on this plot for the moment, ignore the left panel. Here again you have the delta TB on the y-axis, the z on the x-axis. The gray band with the black is again the edges measurement that I showed at the start, and the green model is the bad model that we showed at the start of the talk. But now this blue curve is the model that you get using this inversion process. And you can already see that it's far better fit to the data. Whether you trust this model is another discussion. But we can agree that this model describes the data in a much better way than the model that was developed using our lecture 2 philosophy of postulating a model. Here I have no idea now how this X alpha comes to be, how this epsilon alpha comes, I have no idea. But I now have an epsilon alpha which gets me a curve which passes through the data perfectly. Okay? Yes.
Not done in a static. Not a Bayesian.
Yeah, you could do this in a Bayesian way, but no, this is not done in a Bayesian way. So this is done. These equations are linear, so you are just inverting them actually. That's a good point. Yeah. It's a slightly technical point, so I'm not going into that a bit. You're right. Okay, so then now let us look at what that epsilon alpha is, that magical epsilon alpha, which I could never have got by my lecture 2 modeling style. Okay, because I would not have gone for a boxy shape. This is that, okay, so this is a complicated plot, so let us start panel by panel. Just focus on this right hand side top panel. What is shown in this is the J alpha, the specific intensity. Okay, this is photon number per meter square per second per hertz per steradian as a function of redshift in this range 26 to 40 roughly. Okay, and you first look at this little black curve, this black dotted curve. This is what you would have got had you followed the lecture 2 method. This postulate which connected galaxies to collapse fraction and multiplying that by IMF dependent UV emissivities would have given you that. And we have seen how bad that model was in comparison with edges. And what you get now is this blue curve. You can see that it's dramatically different. Some of the things make total sense actually. For example, what the blue curve is doing is it is saying, oh, at high redshift, just remove all the flux. Which is obvious. If you have too much flux at high redshift, you will do Lyman alpha coupling too soon. Then the edges absorption should have started at much higher redshift. Which is why the data are now telling us, okay, push that to the lower redshift as much as you can. So this is that. And this weird shape is because the absorption that is seen has a weird shape. This shape we would never have recovered in our ab initio, or sorry, our postulatory modeling of lecture. Okay, this is the power of empirical model. This is a very general philosophy in cosmology. Actually, it started by a really well-known idea called abundance matching, which was first used in large-scale structural study. Which was the first time people got tired of creating galaxies that never fit the data perfectly. They fit the data very well, but never perfectly. And then they said, let us ask what kind of galaxies the data wants. And then they came with various empirical modelings. Abundance matching is not the only one now. In fact, Nishikant Khanda in this building has produced beautiful empirical models of the H1 mass function now, which are far, far superior than abundance matching. But that is where this began. Okay, and now this is where, for the first time, Shikhar and I applied it to the 21st century, where you start developing the empirical models of the Lyman alpha. We can do the same exercise for X-rays, exactly the same logic. I won't go into the steps; they are exactly, precisely the same, and you get something like that. But now you can ask, well, you told us about J alpha, but what about the epsilon alpha? Because that is what is connected directly to the galaxies. The epsilon alpha is shown in this book. It is shown in terms of the ratio to the default epsilon alpha. So what is plotted is only this multiplication factor, which in the default model is just 1. No multiplication. You just do whatever we did in lecture number 2. But now you see what it is saying is no. Multiply your postulated emissivity by this complicated function. You see, it is doing some obvious things. It is killing the emissivity at high redshift, m is 0 instead of 1, and then it is introducing this weird shape again to get a weird shape which edges, right? None of this you could have obtained. What you are actually doing here is you're actually seeing galaxies at high redshift, reading out galaxies, assuming edges is correct. You can do the same with X-rays. As I said, here these are slightly different curves where we keep the Lyman alpha same as lecture 2, the default, and say, okay, as much as possible, the X-rays will now absorb the complication required. It's exactly the same process. You can see there are these other curves, and the important thing now is we can ask, okay, so these are the Lyman alpha emissivities and X-ray emissivities we need. How do we get them? Okay. So you see, this is in some sense more rational. Okay, you actually just politely go to nature and ask what is needed rather than forcing what you think nature must do at those redshifts. And then you confront this with our understanding of how Lyman alpha and X-rays are produced. And we found that in none of the stars or X-ray binary models can you produce this much Lyman alpha per unit baryons.
It's got EK.
Yeah.
Then how
It's plotted here.
it is standard for it.
Oh no, here the depth is, in this case the depth is still obtained using the access radio band. Is the shape in this particular calculation? It's the shape that is giving us all this information. So the temperature is not overcooling. You could do that, but if that is not what is done here.
How do I read the emissivity? There's a initial bound, right?
Yeah.
That corresponds to high redshift information.
Yeah. What are you saying? So how do you interpret this? You're trying to interpret this. Yeah, so that's a longer discussion. Essentially, I can say why it needs it. It needs it because the sides of the edges absorption trough are just too steep. So it has to produce a huge amount of X-ray photons in a very short time to quickly heat up. So that is the reason the interpretation is a longer discussion. But the point is, this values of mx and m alpha, we found that none of the published IMFs or X-ray binary models, we are not expert on those. Maybe there are models which do give them, in which case we are wrong. But as far as we can tell, none of the models give them. Okay? But that's a very powerful conclusion that we have now drawn, right? Thanks to the empirical model, that you do need a certain amount of Lyman alpha photons per solar mass of baryon. In fact, then you can do even more. You can say, okay, suppose I now postulate. So I started gaining my ground just a bit. I said, Suppose I now postulate that at least my IMF is universal. The stellar IMF doesn't change that much, unless at cosmic dawn it changes. It's possible. It's not an absurd assumption to say that the IMF doesn't change. In which case I say, okay, my M alpha and MX should be within the range that my IMF models allow. They shouldn't leave that range. But then if you do that, then what the model does is, okay, if you do that, then you must let me change the number of stars that are there per unit volume, because otherwise I cannot get the edges. But that is beautiful, because then that gives us this result. So what, again, focus only on the right panel for the moment. What is shown on the y-axis here is the rho star dot, which I think I showed. I might have showed it in a hurry yesterday, but I think Shikhar also showed in the morning. The star formation rate density as a function of redshift, and this smooth curve, as you might remember from this morning's tutorial, is the default model, is our standard model. But now you can see what edges requires. So if our stars are normal, then edges said, okay, then destroy all the galaxies at high redshift. Otherwise, you will have edges absorption earlier. And then introduce this weird shape because you need a weird shape. You can see what's happening here. You are directly reading a galaxy formation model. You don't know the physics. There is no physics in empirical modeling. You don't know how this curve comes about, but you know the curve. It's a big progress over what we did in the previous lecture. This is a very powerful technique actually in various areas of astronomy in general.
So you get star formation using Lyman alpha, using the J alpha you have obtained. Also, you can count X-ray background, and they. I mean,
yeah, so that's a good question. So we have 2 degrees of freedom to get to.
This X-ray background is also.
So in our model, the excess background doesn't connect to star. The excess background is postulated as the measured by arcade or something. A fraction of that is given to be cosmological value. We don't know what causes excess background. But you are still right that the causal connection is a bit complicated because rho star occurs at 2 places, in the Lyman alpha emissivity and also in X-ray emissivity. So that simple iterative inversion doesn't help you. So here we had to actually come up with a different way of inferring this. Essentially was just a trial and error type way. But it again amounts to in an inversion. And the fact that we were able to come up with one rho star dot means there was a solution that satisfied both requirements.
They're not.
Yeah, they don't impose contradictory requirements. Which is fortuitous. Yeah. Okay, so that was a very important question actually, but it's a detail. But the point is, you get this rho star dot, and again the model is quite good, much better than the default model that we developed in the last lecture. But notice what is happening now. I still don't understand how these galaxies form, but I know that these galaxies have to be there. So I can start doing interesting predictions for things like JWST. For the first time, I think we might have mentioned JWST in this school. There is this amazing experiment which is also targeting the same redshift that we are targeting using 21 centimeter, and this is the first time that we can connect those 2 projects. So here we can look at any of these plots. All of these plots show the number density of galaxies that a JWST survey will see as a function of redshift for various survey limits, brightness limits to which the survey is sensitive, and various field of views. But I think here this is a beautiful work by Shikhar in which he computes. He takes various JWST surveys that are going on right now, Sears, Cosmos, JADES, Primer, WD, and these 2 surveys are infused on the Roman Space Telescope, which is not yet launched. And then let us just focus on the top panel. Here he says what is the number of galaxies per unit redshift that JWST has to find if the assumptions that edges is correct is right. Okay. So you can see that, for example, for Roman, it's a huge prediction. For JWST surveys, there is a small prediction. But what the bottom panel shows is the excess relative to the lecture 2 model. And if the excess relative to lecture 2 model is huge. This paper was written before JWST started producing it, and everyone knows they are finding excess. The obvious next step is Shikhar should sit down and compare this excess with their excess. We have, I think, not done yet, but it would be really nice. But I hope the power of the I didn't want to work. I think Shikhar is going to let you work this model out in the tutorial after PE today. So hopefully you will appreciate this model. But the details will vary from situation to situation. But keep this in mind. This is a very interesting philosophy for modeling 21 centimeter. We don't have to bring our prejudices into the complex physics of these kind of.
This BNDZ?
BNDZ is the number of galaxies per unit redshift. Here basically you can see this number is actually, here you can see Roman should see 10 to 100 galaxies at redshift 14 for this particular survey. So this survey involves specifying the area of the sky that the telescope will see and the faintest luminosity that the telescope will be sensing. So these survey names have all the details. Once you specify the details, you count what is the number of galaxies by integrating all these luminosities. So the luminosity function just tells you the number density of galaxies per redshift per luminosity.
If you access sources, you can also make one days.
Yeah, this is not that level of access. This is access related to the default model. Not that dramatic. Okay, so I think I have spent a lot of time until this point on the cosmic dawn. Which is also what Kanan has exclusively focused on. For his case, the purpose was to understand how global 21 centimeter signal is to be modeled. In my case, actually, the only reason I stuck to cosmic dawn is because the physics is simpler. So what I have been able to hopefully demonstrate to you was a development of a complete model that involves postulating various physical processes for the 21 centimeter signal. And we have seen how subtle that can be. We saw all the complications of the Lyman alpha line. And then now we have also seen a totally different way of doing the same thing using empirical modeling, which only works when you have data. So we use edges. If there is no data, there is no empirical modeling. Okay? So these are the two things. Now I have to leave the cosmic dawn. And now we go to lower redshifts, where we go to the reionization. Now in the reionization era, the spin temperature depends not just on galaxy formation, that continues to happen, it also depends on reionization. There is a new parameter space which opens up, where again I have to do the model. Now here there is no analytical model. There are no analytical models. There used to be analytical models of reionization 20-25 years ago when there were no data, but there is nothing now. The process is complex enough that we have to do it using cosmological simulation. So I will now go through a description of how we model reionization today. And I will highlight some problems, and hopefully some of you will correct those problems and come up with better methods. So the story is again the delta TB is, remember it was a product of these three terms. We have focused on this because it had all the galaxy formation in it. This is the cosmological delta. I'm assuming all of you know how delta behaves using your standard cosmology courses, perturbation theory, all that stuff. And the XH1 is something that did not exist in cosmic dawn. XH1 was just one. It was very simple. And now as we go to the redshift at which Hera, Saurav's experiment operates, we start to worry about XH1. And so XH1 has to be modeled. So as I said, there are no analytical calculations, and we don't actually know what is the best way to model XH1. There are some, everyone has their preferences which can change from day to day. But basically what I am trying to do is describe what the situation is in the field, and I will describe what the basic physics is behind XH1 and how then it is solved to do the calculation. But the solving, first if I just make a general comment, is done in two very different ways. Okay? At the moment, there are some approaches which do XH1 calculation using what are called semi-numerical methods. I'll describe what they are. I will show you an example. And then there are people who do the calculation using an entirely different approach, totally different, absolutely no overlap with each other, which we can call ab initio simulation. And the difference between these two, for those of you who have not experienced these, some of you have done such simulations, they know. But in semi-numerical simulation, what happens is there is no physics. essentially. There are no global physics processes. There are individual recipes. A bit like what we said for galaxy formation in lecture 2. Okay, there are halos, then I have galaxies. How did those galaxies came? No, they just came by a multiplication factor, magically, right? They are very powerful. I mean, we laugh at them, but these are very powerful ideas. But they are at that level. Okay, there is no microscopic physics that actually describes the development of galaxies in a halo. There is a recipe. Whereas in an ab initio simulation, you actually aim to solve elementary physics equation from initial conditions. As you can imagine, that's hard. So indeed, these simulations do very small amount of things than these. So here, for example, you end up with a very large amount of free parameters. This f alpha, f star, fx that we already have in the story. In this simulation, you will have sometimes 20, 30, 40, 50 parameters. Sometimes even those are not enough, and you just say, okay, I will just stop here. I will not introduce any more parameters. Here, there are very small number of free parameters. Actually, the goal of this simulation is to not have any free parameters. That I don't think will ever be achieved, but at least it has very small number of free. Sometimes actually just one free parameter or something. Okay. This is a very fast approach. This is why people have actually followed this. Yes, it calculates XH1 very quickly. This is an extremely slow approach. Then the other important thing is there is no time here. Okay? This might sound very weird, but because there are recipes, I can just say, okay, at redshift 20, I have these F star galaxies. Okay, there is no physical connection between what is happening at redshift 20 and what happened at redshift 21. There is no time variable. There is no dynamics. It's static. I can postulate at every step entirely different thing. I can have jumps. I can have continuities, which can also be powerful. This is what we did in empirical modeling. It can also be powerful by giving you more freedom, but then it can produce inconsistent results. So here, on the other hand, these have a time variable. They are on a light cone. One is there, right? So they are on a light cone. So these are dynamic simulations. These are some of the examples. Probably everyone knows 21 centimeter fast. We tried very hard to set up a tutorial for all of you to use it. We failed, just couldn't get the time, sorry. But email me or Shikhar if you, or Thomas actually has set up 21 centimeter fast over a very wide parameter space. Email him or me if you want to set up this code. But there is also a code called script. There is also a code called Rian Yuga, which people know. On the ab initio side, people might have read papers from the Thiessen simulation suite. We have a simulation which we still haven't come up with a name for, but these are these ab initio simulations. Now, what I want to quickly say is, people get very, it's like, a very political Congress BJP issue here quickly emerges. So, no need to get very emotional about this difference. Think very pragmatically. No need to take very big religious sides here. We actually need both approaches. Okay. So, this approach actually cannot work without ab initio simulation. Ab initio simulations provide some insight, then these approaches copy that insight. Then these approaches give some insight, ab initio simulations copy that insight. Okay, and also one has to remember that don't take my description to mean that these are somehow the right exact God-given calculation. No, these simulations also make some inevitable approximation. They could also be wrong, in spite of being trying very hard to be consistent. They are always ab initio, but they can be wrong. They can be approximate. Okay. So don't feel that one has to do. In fact, one of these. In fact, I encourage all of you, if your redshift of interest overlaps with reionization, to try your hand at both, and you will really enjoy. You will individually learn a lot from both approaches. Okay, I will quickly show examples of both approaches now in the remaining time of this lecture. So let us start first with a semi-numerical model. Again, what is the promise? No time, just recipes. Okay, and magically XH1 will come out at the end. So here is one example of semi-numerical modeling. This is called the famous excursion set method. This is what is used in 21 centimeter fast and script. Okay, so what is, first let me just describe what is being done, and then maybe if necessary we can talk about why it was done like that. So what is done is, you first create a normal cosmological simulation. Maybe a dark matter only n-body simulation, or if you have more computing power, a hydrodynamical simulation. but it doesn't have any reionization or anything. It's just a normal cosmological simulation. Here is an example. So, probably, I assume all of you have done cosmology courses, and this looks familiar. There is a filamentary structure in the density. This is a slice at redshift 7 shown for example. This is a simulation that I did, and the properties of the simulations are given here if anyone is interested, but it's not important. The point is, excursion set method starts by setting up a density. In fact, some methods don't even use a simulation. They use something like the Zeldovich approximation to do this. So you can use any other way as well. The point is, you start with this density. But then what you do is suddenly you jump from there to this map, where you suddenly have this XH1 on the, sorry, XH1 here is called QI, but it essentially XH1 of 1. This is 1 minus XH1, so this would mean completely ionized and completely neutral regions. And so this corresponds exactly to the density slice that I showed on the previous slide. And how did you go from here to there? You had a recipe. Okay, is this recipe valid? That's a big debate which people keep having in the literature. But the point is, this is not a ab initio calculation. This is not a temporal evolution of the radiation field. This is the recipe. Here is the recipe actually. A point is ionized if the number of sources divided by the number of sinks is greater than 1 in a sphere centered on it. Really simple, right? You just take a point, draw many spheres around it. If there is at least one sphere in which all the number of galaxies contained in the sphere, their luminosity, is greater than the number of hydrogen atoms contained in that sphere, then you declare that point to be ionized. It sounds weird, doesn't it? It is weird actually. It's complete. There is no reason for this to work. Okay, it's completely absurd. Yeah. Yeah, these recipes keep improving day by day. In fact, if you look at the excursion code today, right now, if you download 21 centimeter first, it has a far superior version of this recipe. The essence is still there, but it has been modified here, bits and pieces have been changed to make it even better. But I hope you agree that there is no physics motivation, deep physics connection. There was a motivation. Motivation was basically that XH1 is caused by radiation which is produced by sources. If there are many sources in a region but very little hydrogen, then it has to be ionized. That amount of motivation was there, but nothing beyond. But then it produces something like this. So you can debate till the end of eternity whether this is correct. Okay, and then people start going into what does correct mean, and then it becomes a religious fight again. So people, once you start going to these conferences, you will see every time and then there is some older professor who comes and says, no, we need both approaches, blah blah blah, right? So here is a light cone from an excursion set calculation. Here, so now here is an example of what you can do. I said that this is a good method. So what we did here in this paper was to use this kind of a semi-numerical method for XH1 to model 21 centimeter in two distinct reionization histories. One in which reionization is done by galaxies, and another in which reionization is done by quasars. The difference between the two is quasars are very few in number, they are very bright, and they are very clustered. We wanted to ask if this will show up. And the reason we were motivated to do this was there is a big debate about quasars versus galaxies. At least there was a debate around the time we wrote this paper. So but it's very easy. When we do semi-numerical, you just put your quasars in that density field according to some prescription, and then use this radiation prescription to get XH1. This is what you get. Then you put galaxies in that same density field. You again use the same prescription. This is what you get. And this difference was what we were interested in. Okay? And then what we did was we calculated the power spectrum. I could not have, unfortunately, time to go into the beautiful theory of power spectrum, and I actually removed even the material I had prepared because Prasun gave such a nice introduction to the power spectrum and its definition. What he said was precisely how much you need to know for this. But everyone knows that power spectrum happens to be one of the statistics which are going to be measured. Here is the calculation. The point is, here is the model obtained using a semi-numerical. The curve here is the prediction at redshift 7, 8, and 10. These diagonal curves are the sensitivities of various experiments. These measurements are all that was available at that time from the paper experiment. Now, of course, as Saurabh has shown, we have many more experiments. But this is what a galaxy-dominated reionization model gives, and this is what a quasar-dominated reionization model. So in fact, as upper limits, first of all, what we learned was that quasars produce this huge feature at the large scale, up to the 21 centimeter power scale, and you don't see that in galaxies. So when these Hera limits come lower and lower, these quasar models will be the first to be realized. But my point here is not to discuss quasars or something. My point is to give you an example of how the semi-numerical model and how easy it was, right? So if you have some funny model of reionization, you can dark matter annihilation or something like that. You want some quick answers. They will be approximate. They could even be wrong, but they will be quick too, and they might help in getting some intuition. Semi-numerical modeling is what you use. These are error bars on real data. Who asked the question? You asked the question. No, this is a data set called paper, and these are their measurements, and the error bars go out to 0. But because this is a log scale, they look like they look weird. Okay, let me, since time is running out, let me now change my direction and give you an example of the ab initio modeling.
So the expression set method, how do you choose the size of the sphere? So you say that within the sphere it is bigger than 1.
No, you don't switch size. If there exists a sphere, you look at all possible spheres, and if there is at least one sphere where this condition is satisfied, then it's ionized. That's this prescription was developed in 2004 by a person who was a Ph.D. student, Andre Messinger, at that time. This Ph.D. came up with this idea of this process. But it has to be some sphere. We set up 20, 50, 100 spheres, find one of, if one of them works, and get done.
Does this sphere overlap?
No, the spheres are not overlapping. I don't know what overlapping sphere means. They are concentric spheres. Maybe they are 100% overlapping. That is what
Spheres are different.
But you go at each point and do this exercise. So it's very complicated actually. But you can use existing tricks using Fourier transform to make it very easy. You go to each point in the simulation and ask the same question. But it turns out that this is not as difficult. Okay, let me quickly discuss the ab initio bit so that we can finish on time. So on the ab initio bit, what was the promise? Remember, you actually do real physics. You don't have prescriptions now, as much as possible. But you now do real physics. The idea here is you just switch your simulation on, and it will do everything consistently following laws of physics and get you the exception. Of course, that dream I don't think will ever be achieved. But that is the guiding star. That is the aim. That is the ideal that these methods try to always approach as much as possible. Okay, they feel very bad if they don't approach that ideal. So that is the idea. So what's the fundamental process of creating XH1? It's the radiative transfer equation, which I think many others have shown now. Here it is again. Here maybe one difference is I have now included is the cosmological expansion term. But essentially what this does is it shows how this specific intensity ionum evolves along the ray of light. And the source term here is this Jnu, and the absorption term is the kappa. So along the ray of light, the source has emitted some emission, and then it gets absorbed, and then the whole thing is quantified according to this. So when I want to solve XH1, what I have is, what I have to do is, somebody has given me the sources, the galaxies have been prepared for me, or in a model like Thyssen, even the galaxies I will try to do ab initio. But once I have done that, I have to now solve this equation everywhere. So you see, there are no spheres now. You actually find how each photon from each source goes and what does it do in that cosmological box. That is what you are doing. So this equation has to be solved. This equation is very complicated, and in fact it's a partial differential equation. I don't know how many of you have studied partial differential equations in numerical methods or some such courses. But there is one problem in even the simplest algorithm of partial differential equations, in that they have a speed of light limitation. Partial differential equations typically have a delta t variable and a delta x variable, and the time puts, it says that basically your the time evolution of I nu has to be done in time steps which are smaller than the light crossing time of a cell. The light is very fast, so that is a very small delta. Okay, this is called a Courant. This is a very general property of PDEs. Okay, this has nothing to do with radiative transfer. This is called a Courant condition. If you look at numerical recipes or something, you will find a detailed discussion of this condition. The problem is, for us, this delta x is very small because reionization also has a very large dynamical rate. So if you are doing, say, this kind of work in planets or I don't know, galaxies or stars, you probably, this is actually a relatively simpler problem. But here what happens is, our bubbles, the cosmological evolution is over megaparsec scales. That's where the interferometers that Prasun is pointing out are going to work at. But then the delta x, where the gas that absorbs and the sources that produce the radiation are very small. They are kiloparsecs, right? A galaxy is less than a kiloparsec at redshift 10. So then your delta x is very small. So your delta t is very small. So you are absolutely in the worst regime of PDEs here. Okay, you have to do it for many cells. Each cell is small, and you cannot take a big delta. Okay, so this is a huge problem. In fact, if some of you are interested, please talk to me. I am happy to collaborate. I have some ideas in making progress, but this remains an open problem. How to solve this correctly? And a lot of work remains to be done. But a lot of work has also been done over the last 20 something years. So roughly what has happened is many algorithms have come up. They roughly fall into two classes. One is this ray tracing algorithms, where what you do is you actually physically trace rays in the box from each source to each absorber, and along the ray you solve that, you just do brute force basically. Along the ray you solve that PDE. And these were, of course, the early methods, because this is the obvious technique, right? The obvious thing you do when you have specific intensity is raw rays, and you hope that you will find some smart approximation, etc., and shortcut to make it fast. And indeed, these people found many interesting approximations. And the scaling of this method is proportional to the number of cells multiplied by number of sources. The more sources you have, the more rays you need. The more absorbers you have, the more rays you need, right? So basically, there are many famous codes. C2Ray, I don't know if people know, C2Ray is an open code, very well written code, extremely high quality and dependable code by Garrett Menema. But there is also a code called Crash, which uses Monte Carlo, so very interesting approximation to ray tracing. These three codes are in themselves different from each other. They implement ray tracing in different ways, but the basic philosophy is the same. And then what happened was an entirely different approach emerged about 10 years after the ray tracing approach, where people said, okay, what I will do is, I will not draw my rays at all. I will actually solve an approximate version of my radiative transfer. Okay, and these are called moment-based methods. And what they do is they take angular moments of the equation, radiative transfer equations, and then they take the first moment, they take the second moment. In principle, the first moment equation is connected to the second moment. Second is connected to the third, and ad infinitum. You can have infinite such equations. What the moment-based methods do is they say that at high enough moments, I can actually close this hierarchy by making a suitable approximation. This need not have been true, but they showed that this is luckily true. And so now again, what approximation, at what level do you make it, is a matter that keeps getting discussed. This is a philosophy which has been very useful in neutrino transport also, not just in radiation transfer. But at the moment, people have come up with a method called M1 approximation, which is one particular moment-based method. There are multiple moment-based methods. Okay, other famous one is so the example codes here are Aton, Enzo RT, and ART. And Aton and Enzo RT use a moment-based method called M1 approximation. ART uses an entirely different moment-based method, okay, called I'll remember in a second. But it's an entirely different approximation for optically variable Eddington tensor method. That is what R uses. So an entirely different method. Okay, so I won't usual. I have to plan too much. Okay, maybe actually I will go, instead of showing plots, I will just quickly go through the equations to give you a feel, and then the plots you can just take slides from me or ask Shikhar. So I'll just quickly show you. So I have been working with moment-based methods, so that is what I know best. So I will just quickly show you as an example of ab initio modeling of accretion is moment-based method, and I will end the lecture by showing the 21 centimeter prediction. So here is how they work. Okay. The idea is you reduce dimensionality of the problem by taking averages. So you had a 6-dimensional PD, you take average. Angular average will remove the angular variable. Spatial average will remove the spatial variable. So you reduce the dimensionality. This is a very old idea actually. So then the first is you do some basic approximations. You ignore the Hubble term. So this becomes just this. Okay. Again, lots of discussion on whether this is worth doing. The Hubble term is easy to ignore it. Now we take moments. We take angular moments. So zeroth moment, what is how is the zeroth moment described? It is just you take the average over all directions. So you integrate over all directions and divide by 4 pi steradians. And then, for example, the first angular moment of a quantity is one step more than this. There you multiply by the direction. So the unit vector n hat, then take the average over all directions. In the second, you will have 2 n hats, so it will be a tensor. And then again you will take the angular average, and so on. These will be the moments hierarchy. So the zeroth moment of the the radiative transfer equation is just to multiply by d omega and integrate and divide by 4 pi, all those terms. It turns out that the result can be written like this. In fact, so here new terms have. Here the main thing to note is that I nu has gone away. There is no I nu now. Instead of that, you have new quantities n nu and f nu. What is n nu? It's the photon number density. Amazing quantity. It's a local quantity. Photon number density is just how many photons are there at this. So this has units of per unit volume, and this is related to I nu by this moment. Okay. Similarly, you have a new quantity flux, which is now a local vector quantity. It is asking at this point how many photons are going in a given direction. Okay, so this is flux units per centimeter per second, and this is related to I nu as its first moment. So it's not just an integral of I nu with d omega; it's I nu multiplied by n hat and d omega. And now you keep doing this. I have my zeroth moment equation. I now get the first moment equation. First moment equation also you can do the correct calculation. Similarly, what has happened now is the n nu has gone. How do you get the first moment equation? You multiply the radiative transfer equation by n hat and then integrate over d omega. You get this f nu, which is understandable to at least some of us now, because f nu was I nu times n hat integrated, and now you end up getting a new term, which is this p nu, right? This p nu is going to be second moment. Right? Just as n nu equation had f nu equation has p nu, the next level will have p nu equation with the next higher level moment. So p is now a tensor because it has two n vectors, ni and j, and then again integrated over d omega. Here the 4 pi is being absorbed in the units of blah blah blah. But basically, what you end up with a tensor called T. Okay? This is called an Eddington tensor, a pressure tensor. Now you can keep going. In fact, okay, you can. There is no reason to stop. But the M1 method, this is just one method, says okay, stop here. Okay, and what it says is, what we will do is, instead of, we don't know the pressure tensor. For pressure tensor, I will need the next higher equation. But what M1 says is, okay, I will postulate a pressure tensor. Okay? It's almost like a recipe for a semi-numerical method, right? It's almost that kind of crime, right? So you can see the two methods are not, they are both approximate methods. But M1 closure says this is the closure we should use. In fact, if you go and look at this paper, the paper considers many closures and what means, and one can go into the discussion of why this peculiar tensor comes in. But again, it's almost as absurd as that sphere and sources thing. that we have now postulated this pressure tensor, except that this approximation is at a much deeper level in numerics. So we haven't yet left the physics. So maybe that is something better. Here the various symbols are basically the flux and the photon number density. So now we don't have the radiative transfer equation anymore. Essentially, what we have done is replace that with the one equation for m nu, one equation for f nu, and one postulate for p. But this is a closed system. I can now solve this with initial conditions. I know my initial conditions for reionization. Universe was neutral. I know the initial conditions perfectly. I just start there and solve this. In fact, you can see that these are just fluid dynamics equations. That was the beauty of M1, that this actually treats radiation like a fluid. And then there are many advantages of doing that. I'll just quickly go. Yeah, so I think the practical implementation of this for obtaining our XH1 would be the system that I just wrote down will solve for the photon number density at each point, and then at each time step, using those photons, we will solve for XH1 using the chemistry equations. So the photons will go and they will ionize hydrogen with some probability given by the cross section, and you will have these. So this is how this code works. So the code is actually much simpler than any semi-numerical code. It just has these three equations. It solves them at each time step. It goes to the thermochemistry module. It gets the XH1, etc. It takes the next step on the three equations. It goes to the thermochemistry as long as you want. Right? That's it. So you can see the attraction of this method. And you still have the equations in the system. So the intuition hasn't gone. You still have all those variables. And the compromise is this pressure tensor was pulled out of a hat. So this is implemented in a code called Eton, which was written by a Ph.D. student in France. And we have been working with Eton in a while. So for example, for a single source, this produces a nice spherical ionization front, most basic radiative transfer calculation. Very correctly, you can compare this with analytical solutions and it agrees quite well. And this is how reionization works in this kind of an approach. So you can't make a movie like this using semi-numerical method. There is no time in semi-numerics. You can directly get the output at redshift 6 or 7. Okay? Unless your semi-numerical method has time, because we have done some sophisticated adaptations of it. But basic semi-numerical approach doesn't have time. But here you are actually solving photons moving out of sources. Okay? In fact, if you go to very small scales, you will see problems because photons are fluids. There are issues. So in certain cases, this method can give you very wrong answers. But overall, actually, we have found that this method has produced the only model that satisfies all known data about reionization. So far, we keep finding ways in which this model doesn't work. It has some issues. We know that it can't be correct. We know that it has some numerical limitations. The least of it is this pressure tensor, but in the end, it seems to give a correct model. Works very well, etc. And then I'll end with showing the 21 centimeter prediction. This is now the power spectrum as a function of Z for a range of K values. So slightly different way of looking at the power spectrum plot. And what is shown here are all kinds of upper limits from experiment. This is the closest we are. So this is the latest data limit from last year. This star here at redshift 8. And you can see that these solid curves are predictions from this kind of a model of it. You can contrast it with the models that people had previously before we started doing this simulation. You see, it's making significantly different predictions. It is saying, no, take your experiments in this direction, higher frequencies. That's where the peak is likely to be, not at where you stop. The real insights emerge from changing your modeling techniques and learning from each other, etc. In fact, you don't have to restrict to power spectrum. You can go and work on other statistics. So Janaki Raste, who is a postdoc at NCRA, used to be with me in EFR, and made these nice inferences on the bispectrum. And actually, this is a very complicated plot showing bispectrum as a function of K or cos theta, definition of theta. You don't have to worry about the details of this plot, but what we are learning is that this structure has a lot of information. And because we have an ab initio model, we are able to now understand what physics some of these features correspond, right? and so that is the useful. So I think it is time for me to wrap up. I think what we have done, I think 3 lectures are not enough for the modeling, for a leisurely development of modeling. So it was very tough to prepare these lectures, I'll be honest. But I think what we have, I hope, appreciated is that there is no one way of modeling 21st. There are multiple ways, and there is no need to fight with our friends. But the 3 main categories are one is a postulated model, the other is an empirical model for 21 centimeter, and then within the postulated models we have come up with 2 categories of semi-numerical models and ab initio models. We have seen that there are multiple ways in which people are desperately working towards getting a reliable prediction of etc. Tomorrow, once we have the measurement, we will need to use these models for inference. That's where the fight will really break out, where who is right and who is wrong. I think until then we have the time to make progress. So I don't want to give you an impression at the end of this lecture that this is all understood, this is how you do it, then I can write a textbook tomorrow on how to model. Actually, far from it. Every lecture that I gave here, there are a ton of questions which are not yet answered. Overall, modeling 21 centimeter is a thing that we are still learning. So please keep contributing to that discussion in your research. I'm happy to have a discussion. Now in Shikhar's tutorial, he will help you practice some of